Hello, this is Anthony Schmitt for the class ME 3708 Machine Design. Today we're going to talk about gears for the third video topic assignment for the class. So let's get started. Just an overview about gears. One of the main things they do is translate rotational motion. When you have a small pinion gear and a larger gear interlocked with their teeth, the smaller gear will rotate faster compared to the larger one, the one is meshed to, but the torque of the larger gear is proportionally greater. Additionally, the linear speed at pitch diameter will be the same because they're meshed together. And for that portion of the gear is going to move at the same rate as the other. So we have some different kind of gears. Spur gear is the simplest one. Just horizontal teeth. The helical gear is pretty similar, except the teeth are at an angle, and this reduces noise or possible interference. The bevel is quite different. The gears will actually connect perpendicular rather than parallel. And then there's the worm gear, which is definitely strange. Basically have a tube-like gear on top and connected to a regular gear, and because the teeth are angled on the top one, it allows it to translate with the other gear. This is a rack and pinion type of gear, so rather than translating angular velocity, it translates a tangential speed. And to kind of compare two gears with like a pulley system rather, they work very similar. Both serve the same purpose. However, the gear has its advantages because it does not slip like a pulley has a possibility to do. So these are some of the design aspects that we want to consider for gears. First is the gear geometry, how the teeth and the gears appear, and what size and shape they are, etc. The kinematics, how they move together, the meshed gears. With a force transmission, how force is translated between gears, how they produce forces on each other. And then there's stress, what kind of stresses the gears, the gear teeth go through. So let's take a look. So there's some basic equations we might want to use. We'll have the pitch, P, is usually what we start with. Typically, we'll be given the pitch, and you can use the pitch to find the diameter, because N is the number of teeth and D is the diameter. So if you're given the pitch, you can find the diameter that you're looking for based on the number of teeth. And then M is the module. You might be given that as well, and it works the same way. It's just the inverse of the pitch. And of course we have this pitch, which would be pi d over n. Just to compare two kinds of gears, on the left is a more primitive gear. It's just a very, very basic design. It's not fully efficient as you would see on the right, which is a more modern gear, advanced gear. The difference here is the modern gear on the right, it never loses contact, and there's a lot less opportunity for interference that way. And what we call that is the conjugate gear tooth action. It's a modern gear provision that you can see there. There's the conjugate action line right there, and it ensures the angular velocity ratios are constant. The path that it has can be simulated by attaching a string to a pencil on a spool of string and then tracing, and that's the angular path that the gear will take. One thing you want to avoid with gears is interference. Interference is the contact of non-conjugate portions of tooth profiles. So here we can see interference is on the flank of driver during the approach. So as it's approaching the to mesh the wrong portion of the gear to make contact, and it sullies the conjugate action. So with interference, we have NP and NG. NP is the smallest number of teeth that does not experience interference and can be found with this equation. And NG is the largest gear with a specified pinion that is interference free. And here's the equation for that. Now these can also be found using this table. Basically what you do is you'd find M, or perhaps if you're trying to find NG, but you know NP, you can find what NP you have and then go over to the NG, and that would be your value for NG, and then M, you can also find that, which would be NG over NP. Okay, so with gear trains, which is a set of many gears put together into a train to transmit the power or force across many gears, we find that the angular velocity, or small n, is proportional to the number of teeth, and so we can say N3, which is the output, is equal to N2, big N2 over big N3 times N2, the input. And this also works because of the equation we had earlier. It said P equals N over D. So we input PD here, P's cancel, we get D2 over D3 and small n2. Take a look at force analysis on gears. This is the point of mesh with the next gear, and the gears produce forces on each other here, 3 to 2. Say this is gear 2, a gear 3 would be attached here, possibly a pinion, and that's the force that it produces there at that point, which is right here. These are the components, the radial and the tangent, but then there's also the force in the center where it's mounted, which is force FA2, the tangent component and the radial component. Now we can, in order to find torques, we use the equation T equals diameter over 2 times the transmitted load. And a couple ways to find the transmitted load depending on the units. For SI units, it's 60,000 H over pi dN. And then for normal units, it's 33,000 H over V. H is the, say, horsepower, power transmitted, and it's torque times omega, the angular velocity. Here's the Lewis equation for the stress on gears. It's the transmitted load times P over force times the Lewis form factor. And the Lewis form factor can be found with 2xp over 3. The form factor can tell you how many teeth you have, or rather you can use the number of teeth to find the Lewis factor without calculating that equation. This is typically a simpler way to do it if you know the number of teeth. Excuse me. Gears will experience dynamic effects that will change the stresses, so we have to calculate those dynamic effects, and what we calculate is the dynamic effect coefficient, which is kV. There are a number of equations depending on the problem that you're dealing with, and basically we'll just multiply that in with the stress equation. Finally, there's contact durability. The stress from contact durability can be found with this equation squared, and then the elastic coefficient, Cp, is found with this equation, square root 1 over pi 1 minus Vp squared over Ep plus 1 minus Vg squared over Eg. And that concludes the gears topic.